All right, here we go. So related rates deal with as one thing changes, another thing is changing. All right, well, that's all fun. Notice this whole time we've been taking the derivative with respect to time. We're saying, how is this thing changing with time? How is the height changing? Is it getting bigger? Is it getting smaller? How's the width changing? How's the radius changing? How is the volume changing? How's the area changing? All with respect to time. Ugh. So we had to do implicit differentiation because none of the equations we actually have been working with have time in them. So that's annoying. So we have to tack on this little differential everywhere we go. That's why you see a dr dt and a dh dt, d v dt, right? All of these little changes we had to tack on. Last time, so this is when most people were gone, we went through looking at a triangle, right? The height is shrinking, the base is increasing as time goes on. An example of this is if, oh, I don't know, let's say you're remodeling your backyard and they dump a bunch of sand by a wall. The sand like is flowing down. So the height is decreasing, the base is increasing. Okay, so, maybe we're interested in how the area of the triangle is changing with time, or the length of the hypotenuse, or the perimeter, or the angle. Okay, so we went through all these 4 examples. That way we can go through the more confusing word problems. I think I have a worksheet that we can work on next class. Oh my gosh, next class we're going to be in person. I'm actually going to see you guys in real life. It's going to be crazy. It's going to be like Space Jam, where like normally you're 2D, but all of a sudden you're 3D. Okay, so strategy for solving related rates. We went through this last class. We said you have to understand the problem. So unfortunately, it's hard because you actually have to think. You have to be like, what is going on? What do I have? What do I need? And do I have something that relates them? A lot of times it's geometry. So area or volume, surface area. What am I missing? Pythagorean theorem. Just like basic things you already know, but like you have to actually remember it and find the equation. All right, then we take the derivative with respect to time. We plug in everything we have, and then we have to interpret the solution. Like, okay, what does it mean? Does it make sense? So with all that being said, let's cruise on through to a police cruiser problem. A police cruiser approaching a right-angled intersection from the north is chasing a speeding car that has turned the corner, is now moving straight east. This is like a physics problem. When the cruiser is blah north of the intersection and the car is so far to the east, please determine with radar distance between them and the car is increasing 20 miles an hour. The cruiser is moving blah. What's the speed of the car? Okay, so there's a lot of stuff to pull out. So first, let's understand what the problem's going on. There's a lot of words, right? A lot of students are like word problems. So we're going to draw a picture and try to understand it better. Make sure. Okay, yeah, good. I'm recording. Perfect. All right, so we have a police cruiser and approaching a right angle intersection from the north. So from the north means, well, maybe you never look at a map. I don't know. So we have north, south, east, and west. Just FYI. So if we're approaching from the north, we're going from the top down. Okay, so this is Old Popo right here. And then we have a car going east. Okay, so the car is going straight east. So that's to the right. So right here is the car. Okay, so I'm going to draw an arrow so that way I know like where these things are moving in which direction. And it says a right angled intersection, so that means it's at 90 degrees. So this isn't really like a you choose your picture type of story. It's like, no, this is 100%. It has to be this way because they said the police is coming from the north and the car is going straight east. Like, this is what your picture has to look like. It has to be like the right triangle has to look like this. It can't look like this, right? We have to make sure it's going in the right direction. Okay. Okay, so police cruiser, got that. When the cruiser is, okay, remember yesterday when I was crazy and I was talking about like taking a Polaroid little snapshot? That's what this is. This thing, right? We're saying the cruiser is this far north and the car is this far east. This is like a single instant in time. I'm in a helicopter. I take a picture of the location of everything. So let's see, I'm going to write this. So I have the general picture and then I have the snapshot, and I'm separating them because I've realized if I don't do that, people get confused. So I'm separating it. That way we know at a single instant in time versus the general picture. Okay, so when we have our snapshot, this is what it's going to look like, right? So Opopo's here, police, and it is 0.6 miles north. Okay, the car is here. And we have 0.8 miles east. Okay. So I'm going to say this is my Y, this is my X. Right? This is Y, this is X. Okay, so we have the snapshot. I'm just like going sentence by sentence and trying to like understand what is going on. What else do we know? The police determined with radar that the distance between them and the car is increasing at 20 miles an hour. Okay, so that is C, our hypotenuse. Our hypotenuse is increasing 20 miles an hour. So this is our rate of change of the hypotenuse. So dc dt, the rate of change. How fast is the hypotenuse growing? Oh, it's growing 20 miles per hour. So I'm going sentence by sentence, drawing or listing out every single thing told to us, right? This is a lot of information. And last, if the cruiser is moving 60 miles an hour at the instant of measurement, what is the speed of the car? Okay, so the cruiser is going 60 miles an hour. We know the cruiser is going down. It's coming from the north. So in terms of Y, it's going in the negative direction. So our rate of change of the cruiser is negative 60 miles an hour. So since I'm done setting up the problem, I'll see if you guys have questions. And last, what is the speed of the car? So what we're looking for is dx dt, the rate of change of x, the distance from the car, the distance of the car from the intersection. Okay, so we've listed out everything we need. I did not draw this yet. Right, the C, the hypotenuse, is just the distance as the crow flies, as a bird flies straight from the police to the car. Okay, pause, questions. Because once we've drawn it and we like wrote out the things we need to know, for instance, the differentials, dy dt, dc dt, like knowing, oh, this 20 miles an hour, that is this dc dt, right? The rate of change of our hypotenuse. Once we have all this written, you guys could totally finish this problem, right? You know exactly what to do. We have to have a relationship between, y, x, and c. Well, you guys know how to do that. It's just Pythagorean theorem. We know x squared plus y squared is equal to c squared. It's a right triangle. This is true of all right triangles, right? How the sides relate to each other is Pythagorean theorem. So we have a relationship. We need to take the derivative with respect to time. So this, I'm basically following the method that's in the previous page. I'm taking the derivative with respect to time. And notice, nothing is constant. Y is changing. Y is shrinking. The police is getting closer to the intersection. X is increasing. The car is moving further from the intersection. So this means the hypotenuse is also going to be changing. So we're going to have three different differentials, three different like d variable over dt's. Okay, so go through, use power rule for every single term. So we have 2x times dx dt plus 2y times dy dt equals 2c times dc dt. And this probably seems familiar, hopefully, maybe, because we did a Pythagorean theorem problem before in the previous page. All right, all the 2's cancel out because I can just divide every single term by 2. So I'm just rewriting my line without the 2's. Now this is not necessary. It's just makes it a little easier, I guess, to look at. Okay. So if you look at your previous page, like you already know what to do, right? We have this example. I mean, as unlucky it is to be on Zoom during COVID, it is lucky because you're going to have your notes for the test. So that's nice. You're literally going to have an example of every type of related rates problem. So try not to stress too much, just understand the method. How do we go about this? Okay, so we have this line, we're ready to plug and chug. So everywhere it says X, Y, C, these are at our snapshot. We're looking for the speed of the car at that single moment in time when the police car is blah and the car is blah away from the intersection. Okay, I said blah a lot. So X is the distance of the car. The distance of the car is 0.8 miles away from the intersection. We don't know dx/dt, but this is what we're looking for. So I'm going to leave that in pink so it's easier to see. Plus our y value, which is 0.6, times the rate of change of y, which is negative 60 miles an hour, equals c. Ooh, we don't have c, but we can solve for it, right? We know how to do this. Well, Pythagorean theorem time. 0.6 squared plus 0.8 squared is going to be c squared. Maybe you already know what this is going to be. Maybe you recognize it's a 3, 4, 5 triangle. But if you don't, I mean, it's fine. Oops. So we have 1 equals c squared. So c is just going to be 1. It's secretly a 3, 4, 5 triangle, right? If I took a 3, 4, 5 triangle, 3, 4, 5, and I divide every single side by 5, I get 1, 0.8, and 0.6. Once again, math teachers are lazy. It's always 3, 4, 5, or maybe once 5, 12, 13. Okay, so c is 1 times the rate of change, which we said was 20. It's not too bad. This is just computation now, going through order of operations the rest of the time. So let's see. This is 0.8 dx dt minus 36 equals 20. So add 36 on both sides. Okay, this is just computation. So I'm gonna just write out the answer. Let's see, 56 divided by 0.8, so times 5 over 4, or 7, so it'd be 35. dx dt is 35. That's so slow. Let me see if I did this right. Nope, I'm off by a factor of 2. I was like, that seems really slow. Okay, 36 plus 20 is 56. Divide by 0.8 is the same thing as multiplying by 5/4. Yeah, okay. I did by 7, it's 14. Okay, so this is 70 miles an hour. Well, still not super, super fast. But I mean, it's faster than the police guy. And the El Popo. All right. So, I mean, this kind of seems boring, not gonna lie. It's just more word problems. You've been doing them all of your life. But it's, people do this in real life in the sense that, like, I don't know, it's a bad example. Have you ever seen Fast and Furious Tokyo Drift? And there's a scene where the guy's like driving so fast that the police don't even chase him. I mean, if you know, oh, they're literally going so fast, there's no way I can accelerate and catch up, that's useful. But more in real life, for instance, the blizzard that just happened in Texas and people lost water because there wasn't enough water pressure. Well, that's all about regulating 2 different rates of change. The rate at which water's flowing into all the storage tanks and the rate at which water's flowing out and going to the people. The issue was in Texas, there was not enough water flowing in because there's not enough power to use the pumps to pump water into the containers, and people kept using water and there wasn't enough pressure for the water to actually come out of the tubes. Okay, so this is an example of like rates of change. So we have, when we're comparing different rates of change, yeah, having enough water pressure, enough electricity. Those are just examples of people I know of their jobs. All right, any questions over 5? The goal is to like go through many problems so you understand the method. All right. Once again, we draw a picture, understand the problem, come up with a relation between what we know, what we don't know, plug in, solve for the thing we're trying to find. Okay, so water runs into a conical tank at a rate of 9 feet cubed per minute. The tank's stands point down and has a height of 10 feet and a base radius of 5. How fast is the water level rising when the water is 6 foot deep? Okay. Let's draw a picture. So it says conical, not to be confused with comical. It's a cone. That's all it is. This is a cone. It's a tank that is a cone. A little funnel type thing. All right. So this is my little cone. Let's see. We know the rate. Okay. So water's going into the tank at a rate of 9 feet cubed per minute. I'm just going like basically word by word, sentence by sentence. So I drew my tank. I have a rate of change. I'm increasing the volume of water by 9 feet cubed per minute. So the water is going in at this rate. So this is the rate of change of my water. So 9 feet cubed per minute. And this is dV dt because it's a rate of change of volume per time. Volume have units cubed. All right. The tank stands point down, perfect, height of 10 feet, base radius of 5. Okay, so this radius right here is 5 feet. And the height is 10. Okay. And of course, it wouldn't be a real problem without having some water. All right, so there's water here. And water's flowing in. Okay. Height of 6 feet, base radius of 5. How fast is the water level rising when the tank water is 6 foot deep? So this 6 foot deep, this is the snapshot in time. Like at that single instant, take a picture, that instant, that's how high the water is. If you took a picture any other time, it wouldn't be that deep. It'd either be more or less. Okay, so at snapshot, it's going to be 6 foot deep. So where should I put that? Be like at snapshot, I'll just write it. Height equals 6 feet. Okay. How fast is the water level rising when the water is 6 foot deep? So what we're looking for, oops, I'm gonna write that out. We're looking for dH dt. How fast is the water level rising? And H is the, I don't like how I put H equals 10 here. Well, but it is height. Let's put 10 so you know that height is 10. But we're looking for the height of the water level. I'm going to let water level be H because that's actually going to be changing. The height of the cone, not changing. It's a constant height. This cone, it's not all of a sudden like growing, right? This isn't whatever magic land. It's just as we put water in the cone, it's just going to, water level is going to rise. Okay. So we have this information. We have a rate of change of volume. We need height. We have radius of the tank. So really the only equation we know is volume of a cone. So we're going to use volume of a cone. Volume of a cone is 1/3 pi r squared times height. You can kind of think of it as like area of a circle times height. Well, that's cylinder, and then 1/3 because it's like a pyramid cone. And if you're like, I don't care about knowing the equation, that's also fine. It's probably more useful for a math teacher to know than U. Okay, so we have this. There's an issue, right? We have R and H, and this is supposed to be the volume of water, not necessarily the volume of our cone. So I bring that up because when I first was reading the problem, I was like, yeah, R equals 5, H equals 5. But keep in mind, this R and H, this is all about volume of water. And as the water level rises, the radius is going to be changing. The height of the water level is going to be changing. So this is an issue because this is dealing with the radius of the water level and the height of the water level. So I need some way. I don't want it in terms of two variables. This sucks, right? Do we really want to do implicit differentiation and product rule? No, the answer is no, right? Let's take an easier way. So let's make a relationship between radius and height of the water. Okay. So, okay. So I know the overall radius of the cone is 5 and the height is 10. So I just kind of like took a little cross section and it's going to be a right triangle. Throw back to geometry, we're going to use similar triangles and relate them. Okay, now when I'm dealing with the water level is going to have a certain height. I'm going to call H and R of the radius. So we can make a proportion, right? The radius over height should be equal to the overall cone radius 5 over the overall cone height, which is 10. So we can get R in terms of H. So that way we're only in one variable, R. I'm sorry, H. We'll get everything in terms of H. What was I saying? So we get R is, let's see, 1/2 of H. So H over 2. This is just 1/2. So crisscross applesauce, R is H over 2. All right. So we don't have to leave everything in terms of like, now, okay, now we have it in R and H. We can plug in, everywhere there's an R, put in H over 2. That's a really big arrow. So V equals 1/3 pi H over 2 squared times H. So now this is so much better. We have volume in terms of a single variable. Let's see, H squared over 4. It's fine. I don't. Okay, I'm gonna fix this. So 1/3 times 4 is 1/12. So 1/12 pi H cubed. I should show that. Okay, so I showed my intermediate step. So we have 1/12 pi H cubed. Now we can go through, take the derivative with respect to time and like check it out. I don't think I explained myself very well down here in the blue part. So I solved down here, I wrote R as a function of H. That way I'm doing it all in terms of H because I'm looking for dH dt. I don't need R in the equation. I need an H. That way when I take the derivative, I have my rate of change of my height with respect to time. And I have V, it's fine, right? We have dV dt. So I wanted everything in terms of H. That way I would end up with a differential that has H in it. Now the issue is if we would have, had H as a function of R, I wouldn't have gotten the thing I was looking for. That's why I wrote it that way. I forgot to say that. I'm sorry about that. Okay, let's take the derivative. So d dt, take the derivative with respect to time on both sides. All right, derivative of H cubed is 3H squared times, right? Because we're taking the derivative with respect to time, we got to tack on how is H changing with respect to time. So dH dt. And that's what we're looking for. So we're so close. We're so close. Yeah. Okay. We're so close. Let's do a simplify or just plug in. We'll just plug in whatever. Let's do it. So dV dt. So this is going to be at the moment in time. So dV dt is, what was it? 9. equals 1/12 times pi times 3. Our h was 6. Remember at that snapshot, height was 6 times dh dt. Now just get that differential by itself. Let's see. 36 and 12. Yeah, okay, I'll show one more step of simplification. So we have 9 equals 9 pi dh dt. I just solve the numbers. I have 36 times 3, 108 divided by 12 is 9. So 108 divided by 12 is 9. That's how I got that number. Just simplify the numbers and divide both sides by 9 pi. So we have 1 over pi is dh dt, the rate of change of our height. So this is approximately, I know you're dying to find out, approximately 0.318 feet per minute. So, like 4 inches a minute at that moment. So it's not like a lot, but I mean, imagine for a hot second that you are a cattle rancher in the western Nebraska and you're like, yo, let me go feed my cattle as I fill my well. And then, oops, I overfilled my well. Like, you got to know how long it's going to take your water to fill it. Super relatable. All right, so that's 2 problems. We have 2 more. I think we can at least get through 1 more. Let's see which one. Yeah. Can I just go to 50? Yeah, I think we could do both. This is fine. Are there questions so far? Trying to hit all the questions people had last year, like where they were confused. Okay, I think I have this. Yeah, I'm pretty sure I have the solutions to the notes up. All right. I'll let you read the problem. You can give it a shot to draw this out. See which part, if you get stuck, which part you get stuck at. Okay, so I drew a picture. I was hoping, like, I hope you figured out that, like, oh, gotta have a triangle because we have a woman, light shining and my shadow's behind me. Hence, it's a nice little triangle. So I drew a picture. First, I started with the woman, 5.5 feet tall. She walks at a rate of 6 feet per second towards a street light that is 22 feet above the ground. Okay, so I have her, I have the light, and I drew a triangle. So notice that the shadow goes from her to the corner, and then X, I said S was the shadow, X was the distance she is from the light. We want to know what is the rate, at what rate is the length of her shadow changing? So we're looking for ds dt when she's 15 feet from the base. So this is at x equals 15. We're looking for what is the rate of change when she's 15 feet from the lamp. Oh, and one thing I forgot to write, she walks at a rate 6 feet per second towards the street light. Okay, so that's a constant, right? The rate of change is a constant. She's not speeding up, slowing down, she's going at a constant rate. So one thing we know is her rate of change, dx dt. The rate of change of x. Now, this is tricky. So I'm going to make a deal out of it, right? I'm making a big thing out of it. So she's walking 6 feet per second towards the street light. So, from our perspective, she's like, oh, she's getting further from the origin. She's getting closer to the light. The issue is x is defined to be the distance she's away from the light. So as she walks, she's decreasing the distance to the light. She's getting closer to the light. So that's why this is going to be negative 6 feet per second. Because she's getting closer to the light, which means x is shrinking. X is the distance to the light. That's the trick play. Because normally we're like, oh, if you're going to the right, x is increasing. We defined x to be the distance to the light. And since as she walks, she gets closer, x is shrinking, therefore the rate of change is negative. So we drew a picture, we understand what's going on with the problem, we can visualize this woman walking towards a street light. And it's so interesting. Now we need a way to relate things. We're trying to find ds, right? We're trying to find the shadow length. So if there's some way we can relate, the shadow length to something else, and my hint is we just did an example with related triangles. So this triangle up here, we use related triangles to have a ratio, right? We had this small triangle up here, small triangle, and compared it to the big triangle. That's exactly what we're going to do down here. We're using similar triangles. So what this is going to look like, I'm going to use the small triangle. I'm going to use this triangle. So I have, let's do height over width. So we have 5.5 over s, and this is going to be equal to the large triangle, where we have the height, which is going to be 22, over the total width. Well, trick play, the width is going to be s plus x. And I realize my s's look like 5s. I should have picked something different. Maybe like w for shadow. Just try and be descriptive with my variables. Okay, so not too bad, not too bad. We can come up, we can crisscross multiply. That's exactly what we're gonna do. Cross multiply, butterfly method, whatever you want to call it. So I have 5.5s plus 5.5x equals 22s. This is chill, right? Move all your s's on one side. Get it by itself. Uh, 22 minus 5.5, so 16.5. So we have a relation, right? We came up with similar triangles. We crisscross, simplify as much as possible. The next step would be to take the derivative with respect to time, plug in, and solve the thing that we want, the rate of change of the shadow. So let's take the derivative of both sides. So I used chain rule. I kind of just went fast with this line. The derivative of 5.5x, 5.5. But we're not taking the derivative with respect to x, it's with respect to t. So we had to tack on dx dt because we have to know how is x changing when t changes. Okay, same thing on the right side. Derivative of 16.5s. Oh, that's just going to be 16.5, but we got to take into account how is s changing, how's the length of shadow changing with respect to time. So tack on ds dt. Right, so we quote unquote are like tacking on these extra differentials when we're taking a derivative of a variable that's not the one we're taking with respect to. That's not the variable that's on the bottom. So I know they say I've said this a lot, but like, don't want you to make that mistake, and I want you to know when do you use it, when do you not. All right, we have everything we need. We just got to get ds dt by itself. 5.5 times -6. I'm just gonna do it in one shot, one go. 5.5 times -6 all over 16.5 is gonna be ds dt. I divided both sides by 16.5. So let's see, 33 divided by 16.5. Oh, that's 2. Okay. -2 feet per second, feet per second. And if you're like, ooh, I forgot where the units, just look back in the problem, feet per second. So it means, so note, we didn't use x equals 15. It didn't matter. The light is not moving. That light pole stuck in concrete. She is not like running or accelerating. She is going at a constant speed. So what this tells us is it doesn't matter how far away she is from the light. This is how fast the distance is shrinking. It's because she's not, getting faster and faster and faster, slowing down as she goes to the light pole. She's going at a constant rate. So the distance between her and the light is going to shrink at a constant rate as well. Right? It didn't even depend on x. It didn't depend on it at all. So, all right, uno más. One more. Wonderful. All right. Yeah, that took about 10 minutes. This last one will take 10 minutes. And you guys get a longer weekend. Well, I guess Libby does. You guys have something Monday. All right, seems like you're still writing a little bit, so I'll wait a moment. All right, last page of the notes. Let's get it. All right, water is being poured at a rate 25 cubic centimeters per second to a cylindrical glass. Blah, 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 height, blah, radius, blah, blah, blah. All right, let's draw a picture. You know what this reminds me of? I started making homemade kombucha. So, 2 days ago, I was like, oh, gotta change the batch. And so talking about water being poured, I've made new tea and then I accidentally poured half of it in my sink. So that was unfortunate. All right. Every time it's like blah, blah, blah cylinders, I got to think about my kombucha. Oh my gosh. I could probably have some brewed and we could have a kombucha party the last day seniors are here. It's not kosher. Or if you don't like kombucha, that's fine. Okay. Glad I'm recording this. Water is being poured at a rate. Is this right? Cubic cylinder. Okay, this is cylinder glass. Perfect. Base radius of 20 centimeters. So this guy, 20 centimeters. Height of 100 centimeters. Wow, that's huge. It's a whole meter tall. That's huge. Okay. At what rate is the depth of water changing when the glass is half full? Okay. Let's see. So my water is half full. Right. Here's my water. And if the water is half full, guess what? That means the, no, that's not what we want. Water is being poured. Oh, okay. So dV dt, the rate of change of the volume is 25 centimeters cubed per second. Just pouring water in this much every single second. We want to know at what rate is the depth of the water changing. Okay, depth of the water, this is dH dt. Because the height of the water is h. We did a problem very similar to this 13 minutes ago. Ish, kind of. We did a cone. This is a cylinder. So the volume of a cylinder, pi r squared times height. Literally base, area of a circle, times height. Okay, that's chill. Difference is our radius is not changing. Our radius is 20 centimeters every single time. It's a cylinder, right? The radius of the water is gonna be the radius of the container. It's not changing. It's not like a cone. This is a cylinder, constant radius. So that's why I'm like, yeah, we could totally finish this one because I just plug in 20. That's it. Plug in 20 for radius. It's not changing. It's gonna be the same radius as the cylinder. All right, let's simplify this out a little bit. 20 times 20 is 400. So we have 400 pi times h. All right, take the derivative of both sides with respect to time. Because we know how fast the volume is changing with time. Let's figure out how the height of the water is changing with time. So 400 pi, that's a number. Pi is a number, 3.14, blah, blah, blah. So 400 pi is a constant. So it's like 400 pi times h. So I have the constant up front and then have to tack on dH dt. So this means, should I do this now or later? No, let's okay, we'll plug in and then we'll do the step. I'll show that. So I plug in, so at the time we're interested in, our volume is changing 25 centimeters cubed per second. We have 400 times pi times dH dt. Notice it doesn't depend on height, not at all. I'm pouring in a certain amount of water every single second. Doesn't matter what time. It turns out the height is going to be changing at the same rate. All right, times dH dt. So divide by 400 pi on both sides. dH dt is, right, the rate of change of the height of the water is 25 over 400 pi. We can do better than that. So divide by 25 on the top and bottom. Let's see, how many quarters are in $4? 16. So 1 over 16 pi. Maybe that still is not very interesting. So you say 1 over 16 pi centimeters per second. Or if you're like, nah, I need a number, you could plug into your calculator. 0.0199 centimeters per second. So literally it's no, not even a millimeter. It's really, really nothing. Like a fifth of a millimeter per second. So it's very, very slow. Because this is a huge tank, very large. So that's it. All right, we finished the notes. We got like 4 or 5 minutes. If you have questions, we can go over it. Okay, so I think I only put like 2 days to go over this lesson, whatever, it took us 3. We'll definitely do a worksheet next class. I know Jesse Rose, you won't be here. If it took us 3 days, I think we should, okay, I hate to do this, but let's do it. We have class on the 14th. Nope, that's next week when you're gone. Okay, 19th. We have school on the 19th, which is Monday. I'm gonna move the test to the 19th. It's gonna be a little brutal, not gonna lie. It's gonna be the first time. Oh, wait, you guys won't even be here because it's 9th and 10th grade. Oh my God. It's fine. Everything's fine. It's fine. World's on fire. It's fine. We're gonna have the test on the 19th because I'd like 2 days to like actually have 1 day to go over a worksheet with just more examples of this and 1 day to do the practice test. There it is. You just push things and push, but at least then you'll understand.
So it's just like a normal
Rose,
test,
what'd you say?
like how. So it's going to be like a test like we've been doing online, like those, like
Yep,
how we print it.
because you guys are gonna be zooming in. Great. I wanted it to be in person, but it's fine. It's all fine. Okay, so that's it for today. I was so excited. I was like, oh my gosh, we'll have everyone was taking it at once, all online. Okay, well, that's it. Shabbat shalom. I mean, have a good weekend. This is it. I'll see you guys next Wednesday. Wow.
Thank you.
See ya.
Ah, oh.
I'm
Everyone
stop
is so quiet.
recording.